Thank you for being here. My name is Robert Larsson, and I'm from Lund University, in the Department of Structural Engineering. Lund University is in Sweden. And this work has been done in collaboration with my colleague Mathias Haage, who is also at Lund University at the Computer Science Department. So concrete pumping is a very common construction method, especially in urban areas. And it's a very efficient way to transport and move concrete vertically. And this is especially important when it comes to high-rise buildings. And to move concrete from ground level up to the high levels involves high pressures. As you can see on this slide here, this is a typical setup of a pumping session. You can see the boom arm stretching from the concrete pump at the ground level up to the floor where concrete is poured. And the boom arm carries the distribution pipes in where concrete is pumped. And concrete exits at the end of a flexible rubber hose, which is called an end hose. You can see that in the center here. And the end hose is manually directed to point at the location where concrete is intended to be placed. And this is done by a human, a so-called hoseman. And you can also see other workers close to the end hose responsible for height control, leveling of concrete, and vibration. And overlooking the whole process, we have the boom arm operator, and he's responsible for positioning of the boom arm and also keeping track of the pumping pressure. However, the method is associated with some risks when it comes to especially for the person that handles the end hose. It's quite heavy to move it, especially when it's filled with concrete, and it's a risk of, you also need to balance on rebars, which could be covered by concrete. So there is an obvious risk of tripping or falling down. But the third one is perhaps the most serious one. There's a risk of sudden pressure buildup in the system, which cause air voids to distribute in the system, and when these air voids exits the end hose, it can cause very strong movements. And this is very dangerous, you can imagine, if you're close to that end hose, and you can get serious injured. And there are even death accidents reported on this. So our main topic here is actually to remove the need to manually handle the end hose, and to remove as much people around it as possible. So we are proposing a robotic end hose. And this solution comprises of 4 air muscles that are attached along the end hose by 2 lightweight fixture plates, one at the top and one lower down along the end hose. So when air is inserted into the air muscles, they will be pulled together and acts as an external force on the end hose, making it bend in some direction. So by controlling which end air muscles that are supplied with air, we can also control the movements of the end hose. So we have developed a PLC unit for that to control the flow of air to and from the air muscles. And to control the PLC unit remotely, we have also a radio control device. And we have used here in this setup an external compressor unit to supply the system with air. And the research was divided in 3 stages. We started with a pre-study looking into the functional requirements of different solutions, and we here involved experts in concrete pumping technology, in mechanical engineering, and robotics. And we come up with a solution that we believe were good, and we tested it in our next phase in laboratory, especially focusing on the behavior of the air muscles and the configuration of the air muscles. And when we were satisfied with that, we moved on to do a field test where we test this prototype under real conditions during concrete pumping. And afterwards, we did a seminar where we invited industry experts to have a view on this test and provide feedback. And this feedback we intend to use in our further research. So this is a picture of the field test. It was a foundation slab comprising 9 cubic meters of concrete that was poured. Standard concrete were used, and also standard concrete pump. We used an end hose with a diameter of 4 inches, which is quite common, and a total length of 4 meters. And we used also then a small external compressor unit. The organization was that we have one operator responsible for remotely control the end hose, and this person got 50 minutes of pre-training before the pumping started. And then we have one person responsible for the boom arm and 2 workers on the ground responsible for vibration and surface finish. So here we can see some of the results. It was quite successful. We managed to use the remote control of the end hose in more than 90% of the total pumping time. The productivity rate was calculated to be a little bit better than manual pumping. We, though, observed some improvements of the speed of the end hose that we should address in our further research. We also think that the need for adjustments of the remote control to make it more intuitive during steering would be appropriate. And in overall, it was quite easy to attach and detach the robotic device to the concrete pump. It took less than 5 minutes to do that for 2 people, so no major issues there. So to conclude here, we think that the tested setup worked very well, considering this was a first-of-a-kind test. The tested system did not lower productivity, but it significantly improves safety, since 90% of the time we can manage the remote control of the end hose. And we have, though, discovered some considerations that we will address in our further work. And the longer-term issue is to integrate the remote control of both boom arm and end hose. So with that, I would like to express my acknowledgements to the project funders of this research and the companies involved in this. Thank you for listening.